Welcome to Core Programming Thinking. Today, we're going to understand one of the most important concepts in programming: time complexity and space complexity. Many beginners focus only on making their code work. Professional developers focus on making their code work efficiently. Imagine you have a list of 10 numbers. Searching through that list is easy. But what if the list contains 10 million numbers? Suddenly, efficiency becomes very important. This is where time and space complexity help us. Let's start with time complexity. Time complexity measures how the execution time grows as the input size grows. Notice something important. It does not measure actual seconds. Instead, it measures how the amount of work increases when more data is added. Let's use a simple example. Suppose you have a box containing 100 number cards. You want to find card number 75. One approach is to start from the first card and check each card one by one. Maybe you find it after checking 75 cards. Maybe you find it after checking all 100 cards. This is called linear search. As the number of cards increases, the amount of checking also increases. In programming, we write this as O of n, or simply ON. The letter N represents the input size. If the input doubles, the work roughly doubles. Now let's look at a faster approach. Imagine the cards are already sorted. Instead of checking every card, you go directly to the middle. If the number is larger, you ignore the left half. If the number is smaller, you ignore the right half. You keep repeating this process. This is called binary search. Instead of checking every card, you eliminate half of the remaining cards each step. For 1 million items, you need only about 20 comparisons. That's incredibly efficient. Binary search has a time complexity of O log n. Don't worry about the math. Just remember that O log n grows much more slowly than ON. Now let's look at another common complexity. Suppose you have to print every number in a list. If there are 10 items, you print 10 times. If there are 100 items, you print 100 times. This is still ON, very common and usually acceptable. But what happens if you have two loops nested inside each other? For example, for every student, you compare them with every other student. If there are 100 students, you perform 100 times 100 comparisons. That's 10,000 operations. This complexity is called ON squared, written as O in superscript 2. As input grows, the work increases very quickly. With 1,000 items, you now have 1 million comparisons. This is why nested loops often become performance problems. Now let's discuss space complexity. Space complexity measures how much memory a program uses as the input size grows. Think of memory as storage space. Let's say you receive a list containing 1 million numbers. If you simply read the numbers one at a time, you don't need much extra memory. Your space complexity might be O1, also called constant space. Constant space means memory usage stays roughly the same regardless of input size. Now imagine you create a second list and copy all 1 million numbers into it. As the input grows, the additional memory grows too. This is ON, space complexity. The larger the input, the more memory you consume. Let's compare two examples. Example 1. You calculate the sum of all numbers in a list. You only need a single variable called total. Regardless of whether the list contains 10 numbers or 10 million numbers, you still use one variable. This is O1 space. Example 2. You create a new list containing doubled values from the original list. If the original list has 1 million elements, the new list also has 1 million elements. Memory usage grows with input size. This is ON space. Now here's an important lesson. Sometimes faster programs use more memory. Sometimes memory-efficient programs take longer to run. This is called a trade-off. For example, caching results in memory can make a program much faster. However, it also increases memory usage. As developers, we often balance speed and memory depending on the situation. Let's talk about the most common complexities you'll encounter. O1 means constant time, very fast. Examples include accessing an array element by index. O log n means logarithmic time, extremely efficient for large data sets. Binary search is a classic example. ON means linear time. The work grows proportionally with input size. O in log n is common in efficient sorting algorithms. O in superscript 2 means quadratic time, usually caused by nested loops, can become slow for large inputs. O 2 to the power n and O n factorial are extremely expensive. These appear in certain recursive or brute force algorithms. We generally try to avoid them when possible. Here's a practical mindset. Whenever you write code, ask yourself two questions. First, how many operations will this code perform as data grows? Second, how much extra memory will this code require as data grows? These two questions help you think like an experienced programmer. Remember, time complexity is about speed. Space complexity is about memory. Neither one is always more important than the other. The best solution depends on the problem you're solving. As you continue learning programming, don't just ask, does my code work? Also ask, will it still work efficiently with 1 million records? That simple question is the beginning of professional software engineering thinking. And that is the foundation of understanding time complexity and space complexity. Thank you for listening.